In this video, we'll learn how to graph linear inequalities in two variables. So first, let's take a look at an example of a linear inequality in two variables. So we see that these look very much like linear equations in two variables, except the inequality symbol replaces the equal sign. So let's talk about the meaning of this statement and what the solution set looks like. So here we have x plus y is less than or equal to 5. Remember, the solutions to an equation in two variables are written as ordered pairs, x comma y. So we want ordered pairs that make this statement true. So the sum of the x and the y coordinates could be equal to 5, or the sum could be less than 5. So let's make a list of some of the solutions for this inequality. So here I just have rewritten the inequality, x plus y is less than or equal to 5. So I might be thinking about values that are equal to 5. I'm just, brainstorming here some possible x values. So let's say x is 1. If I want to be equal to 5, then y would have to be 4. I could also have ordered pairs like 2, 3. I could change the order of these ordered pairs and put 4, 1, 3, 2. I could have some negative x values. So let's say x is negative 6. Then the y value would have to be positive 11, so that when I add these together, it would equal to 5. But this only is really looking at the values where the sum is equal to 5, and there are more of these, right? So this keeps going. If we want to look at when we're less than, let me label these. So let's say this is the equals case, and I can look at the less than case. So if I want the sum to add up to something less than 5, it could add up to anything. 0, 0 is a solution. If I add those, it's less than 5. 2, 1 is a solution. Negative 6, negative 7 is a solution. And there are lots more solutions. 10, negative 7 would be another one. Those add up to something that is smaller than 5. And I could keep this going as well. Both of these lists are going to be infinite. But when I start to plot the points for these for the solution set, I'm going to see I'm a little bit all over the place. So let's go ahead and do that. All right, so I'm going to put these side by side as best I can here, and we're going to start to plot some of the ordered pairs that we have listed. I'm going to start with the ordered pairs that are equal to 5, like 1, 4. So 1 and then 4 lives here. 2, 3. 4, 1. 3, 2. And I also have negative 6, 11. Let's see if that fits here. Negative 6. And then I'd be up to 5, 6, 7, 8, 9, 10. 11 would be just off my page. But I get a sense of where these points are going when we're equal to. So if I looked at x plus y equals 5, we already know how to graph this. Right? We know that the solutions to that are a line. So I'm going to go ahead and draw that line in because I have enough points I can tell where the line lives. I also know that 5, 0, 0, 5, all of those are solutions. So this line will live here. And that represents the equals case. Now the other solutions are not when the sum is equal to 5, it's when the sum is less than 5. So let's see where those fall in relation to the line. So the first one I had thought of was 0, 0, 2, 1, negative 6, negative 7, 10, negative 7 as well. So that lives over here. So if this line were to keep going, it would look like that, just to get the relationship. So no matter what points I pick, if I start picking some more points that add up to something smaller than 5, I'm going to see that they're all going to be contained on this lower left hand corner, or this side of the line. And that's really true whenever we're graphing linear inequalities. We're going to see that we'll have some sort of boundary line, and then all of the solutions will live on one side of that boundary line. So if I kept this list going and found all of the possible ordered pairs that add up to something smaller than 5, I'm going to see that I would eventually plot every single point that lives on this region of the line. This is what we call a half plane. Because our plane is an infinite sheet of paper, our line is infinite as well. So no matter where the line lives, you can think of it as cutting that plane into two pieces. And since they're both infinite, we can think of them as two equal pieces. So no matter what line I draw, if I shade on one side of it, I'm really shading a half plane. So here I'm shading the lower half plane in relation to that line. And the shading just represents all of the solutions because I can't possibly plot every single point in that shaded region. I just shade the whole thing to show that it's everything on that side. All right, so now let's talk about what happens when I take the equals out. All right, so in this I have the same inequality except for the fact that I'm just strictly less than 5 and not equal to 5. Well, in the example that we had, the equal to were these points here. So now if I'm thinking about x plus y is less than 5, I'm really removing all of the points that are on this line. But all of the other solutions are there, and that boundary will still be there. So the way that we would represent that would be, instead of drawing in that solid line, because that solid line means I'm including all of those points, I would draw a dashed line because I would want to show that I'm up to that line but not including that line. It's very much like when we graph something on a number line and we shade one side and we say, all right, we get up to but not including 5, so we're maybe put an open circle at 5 and shade on one side, or put a parentheses at 5 and show that we're not including that. We're getting really close to that. It's the same idea for inequalities in 2 dimensions on the coordinate plane. Right, so in general, here's your definition for linear inequalities in 2 variables. A linear inequality in 2 variables is of the form ax plus by is less than c, where a, b, and c are real numbers, a and b are not both 0, and that less than symbol can be any inequality symbol, less than, greater than, less than or equal to, greater than or equal to. Right, so let's take a look at this first example, how to graph in general, but looking at another inequality, y is greater than or equal to 1/4 x minus 2. So as we just saw, we're going to have some sort of boundary line. This case, we have the equal to, so that boundary line is going to be included in the equal set, and then we'll have some sort of half plane shaded either on one side or on the other side of that line. So here's a representation of the solution set for this inequality. Notice my boundary line here is a solid line, has a y-intercept at -2, as a slope of 1/4. Right? So I go up 1 unit, 4 units to the right to plot another point on that line, and that's one way I can get the line down. Solid once again because it's equal to, and then I want to shade all of the points that are included in the greater than piece. One way that you can get the shading is by doing something called a test point. So I can test any point that is not on the line and see if it makes the statement true or false, and that can help me indicate which side of the line should be shaded. So one test point that I always recommend that you try to use whenever possible is 0, 0, because this is just an easy point to plug in because we have zeros, and zeros are easy to multiply by and they're easy to add and subtract with. So let's test 0, 0. Here's my inequality. So we're testing 0, 0, plugging in 0 for x and for y. And we just want to know, is the statement true or false? So I'm going to simplify each side. 1/4 times 0 is 0, minus 2 is -2. And I want to know, is 0 greater than or equal to -2? And yes, it is, because 0 is further to the right on the number line. So if this is true, that means that the side of the border line, or that boundary line that contains that point 0, 0, is the side that I'm going to shade. So you see here, there's my test point 0, 0, and I would shade the side that has that test point. We're going to see that there's some other ways that you can determine which side of the line to shade. One other way would be to look at the inequality symbol. This only works, though, if your inequality is solved for y. So if you have y isolated and the coefficient of y is positive 1, you can use the inequality symbol. If it's greater than, you'll be shading above the line, and if it's less than, you'll be shading below the line. Now, sometimes, depending on the steepness of your line, it can be kind of hard to tell what is greater than and what is less than. So you kind of have to maybe use that test point as a backup. Okay, so in general, when we're graphing linear inequalities in two variables, we're doing two things. The first thing is to graph the boundary line. So if you have a strict inequality like less than or greater than, you're using a dashed line or a dotted line. If you have a non-strict inequality like less than or equal to or greater than or equal to, you're using a solid line to show that that line is included in the solution set. Then you're going to shade the half plane that contains the solutions. So you could use a test point as I just described. You could use any point that's not on the line. So it's really important that the test point is not on the line. If the test point works, shade the region that includes that point. If the test point doesn't work, you shade the opposite region, the opposite side of that boundary line. In the next video, we'll take a look at some examples and we'll graph them.